National 5 Mixed Electricity Problems. A student sets up the following circuit. Calculate the current in the circuit. First of all, let's look at the values we have. Up at the top, we've got 15 volts there. We've also got some resistances, and it's the current we want to work out. So, the voltage is 15 volts. The current has a little question mark, and our resistance is 15, 30, and 30. You can see this question is worth 4 marks, so it's not just an equation we're going to use. We've got another step here. The step to recognise is that we need to find the total resistance in the circuit. And because this is a series circuit, the total resistance is going to be R1 plus R2 plus R3, which is 15 plus 30 plus 30, which is equal to 75 ohms. Because we've got voltage, current and resistance, we can use Ohm's law to solve this question. So V equals IR. Filling in our numbers, we've got 15 equals our current times by 75. Rearranging this, our current is equal to 15 divided by 75, which gives us a final answer of 0.2 amps. Part 2. Calculate the potential difference across resistor 1. So you can see it's worth 3 marks this time, so it is just an equation we're going to use. There's no extra steps in there. So potential difference, that's where we want our question mark. We have a current, which we just worked out, that's 0.2 amps. And the resistor that we're using is resistor 1, that's this resistor just here, so our resistance is 15 ohms. Again, using Ohm's law, V equals IR. V equals 0.2 times by 15. And popping this into a calculator, we get our potential difference equaling 3 volts. Part 3. Calculate the power dissipated in the 15 ohm resistor. So we want to calculate power, and we know it's in the 15 ohm resistor, so that's our resistance. We worked out the current earlier in the question, so that's 0.2 amperes. And we just worked out the voltage for this resistor, which was 3 volts. So we've got 4 values here. We can actually use 2 different equations for this question, and both would give us the correct answer. So I'm going to show you how to do it both ways, and you'll hopefully see that giving us the same answer means we could use either of them. So we've got either P equals I squared times R, or we've got P equals V squared over R. Let's try P equals I squared R first. So P equals 0.2 squared times by 15. That gives us an answer of 0.6 watts. Looking at our right-hand equation, we've got P equals V squared over R. So that's going to be equal to 3 squared divided by 15. And again, that gives us 0.6 watts. So you'd only need to use one of these methods. Either equation would work, and it'd get you all 3 marks. Part B. The circuit is now rearranged as shown below. State how the reading on the ammeter compares to your answer in A part 1 and justify your answer by calculation. You can see this is worth 5 marks. So your equation is going to be worth some of those marks, and then you need a statement at the end stating what you think is going to happen to the reading on the ammeter. So you can notice now that instead of having the 3 resistors in series, 2 of them are in parallel. So this means we're going to need to recalculate our total resistance, because the total resistance is going to have an effect on the reading on the ammeter, which is the current. So looking just here, we have 2 resistors in parallel there. So remembering our equation for resistors in parallel, 1 over our total resistance, which I'm going to label RP there, resistance in parallel, is equal to 1 over R1 plus 1 over R2. So 1 over our total resistance in parallel there is 1 over 30 plus 1 over 30. Our denominators are the same, so all we need to do is add the numerators, so that gives us 2 over 30. Now we need to flip our fractions or cross multiply, whatever you feel more comfortable with. So I've got RP over 1 equals 30 over 2, so I flipped my fractions. We know that RP over 1 is just equal to RP. 30 divided by 2 is 15, so our total resistance in parallel there is 15 ohms. So now we want to calculate the total resistance, so that's including this resistor on the left-hand side. So our total resistance is 15 ohms that we just calculated, add on this 15 ohms just here. So our total resistance there is 30 ohms. Previously, our total resistance was 75 ohms, so our resistance has decreased. Therefore, because resistance is the opposition to the flow of current, our current will have increased. So a decrease in resistance means an increase in current. So that final statement will get you a mark there. Your first mark would be for the first part of the equation, just here. Second mark would be showing this section just here, so the 1 over 30 plus 1 over 30. Your third mark is showing that your resistance in parallel is equal to 15. Your fourth mark is adding on the extra 15 to get to the 30 ohms altogether. And then your fifth mark is this section of writing just across here. Let's look at a different question. A toy car contains an electric circuit which consists of a 12-volt battery, an electric motor, and 2 lamps. The circuit diagram is shown on the right-hand side there. Part A. Switch 1 is now closed. Calculate the power dissipated in the motor when operating. So looking at our circuit diagram just there, if we close switch 1, our circuit comprises of our battery at the top and our motor, because switch 2 is still open. We can ignore those 2 lamps. So to calculate the power, we know that there's a voltage of 12 volts, and we know that the resistance is 100 ohms. We don't need to take into account any of the other resistances, it's just the motor resistance we need to take into account. Using these 3 values, we know that the equation we'll need to use is P equals V squared over R. And then plugging in our numbers, we've got P equals 12 squared over 100. So P equals 1.44 watts. Part B. Switch 2 is now also closed. Calculate the total resistance of the motor and the 2 lamps. We can see that the motor and the 2 lamps are in parallel, so we'll need to use our equation 1 over our total resistance equals 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So plugging in our numbers, we've got 1 over our total resistance equals 1 over 100 plus 1 over 50 plus 1 over 50. Now we need to make our denominators the same if we go through the fractions method. You could just pop this into a calculator if you wanted to, but I'm going to show you how to use your fractions. So left-hand side stays the same, 1 over RT. We need to look at our denominators and decide on a number that we can use there. So we need a number that will divide by all 3 of our denominators that we've already got. I'm going to choose 100 because we've already got one denominator that looks like that. So 1 over 100 is going to stay the same. Then we've got something over 100 just here. 1 over 50 is the same as 2 over 100. Whatever we do to the bottom part of the fraction, we have to do the same to the top. So we multiply 50 by 2 to get to 100, so we need to multiply 1 by 2 to get to 2. Now we need to add up our fractions. So 1 over RT equals 5 over 100. Now we're going to flip our fraction or cross multiply. I'm going to flip my fraction, so RT over 1 equals 100 over 5. Therefore, our total resistance equals 100 divided by 5, which is 20 ohms. Remember, if we want to cross multiply, I'll just put that across at the side here, we would times 100 up on this side and our total resistance up on that side, so we'd get 100 times by 1 equals RT times by 5. Then we take RT over to the other side, so we've got, oh not RT over to the other side, 5 over to the other side, so we've got RT equals 100 over 5, which again is the same as before, that equals 20. Part 2. One of the lamps now develops a fault and stops working. State the effect this has on the other lamp, and you must justify your answer. So because we can see that the motor, the first lamp and the second lamp are in parallel, if we got rid of, say, this lamp just here, the other lamp is going to stay on. And that's actually all we need to say just here. So our first point can be the other lamp stays lit, or on, and this is because the lamps are in parallel. So I've written two sentences there, it's worth 2 marks, so I'd get a mark for each one. And we've got another question just here. A thermistor is used as a temperature sensor in a circuit to monitor and control the temperature of water in a tank. Part of the circuit is shown here. A. Part 1. The variable resistor R is set at a resistance of 1050 ohms. Calculate the resistance of the thermistor when the voltage across the thermistor is 2 volts. So we've got a bunch of different numbers there. Let's have a look at them to make it a little bit more easy to interpret. So we have a resistance of 1050 ohms just there. We have a voltage of 2 volts. And we have, in our diagram, we can see a total voltage of 5 volts there. So annotating our diagram, it says the variable resistor is set at a resistance of 1050. So our resistance here is 1050 ohms. We want to calculate the resistance of the thermistor, so this is what we want to work out, when the voltage across the thermistor is 2 volts. Up at the top here, the variable resistor R, we can actually work out the voltage just here because we've been given the total voltage. So the voltage across the variable resistor is going to equal the supply voltage minus the voltage on the thermistor. So our voltage over our variable resistor equals 5, take away 2, easy peasy that one, we've got 3 volts there, so we can put that in here. Now you can see we've got one value missing there. If I put some numbers to these, let's say we call the thermistor 1 and the variable resistor 2, I can put some little subscripts here, so R1, V1, R2, V2. This now looks like an equation that we can use. V1 over V2 equals R1 over R2 from your equation sheet. Plugging in some numbers, we have 2 over 3 equals R1, which is what we want to work out, divided by 1050. Rearranging this, we get R1 equals 2 over 3 times by 1050, and that gives us an answer of 700 ohms. Part 2. The graph shows how the resistance of the thermistor varies with temperature. Use the graph to determine the temperature of the water when the voltage across the thermistor is 2 volts. Looking back at our previous question, we know that when the voltage of the thermistor is 2 volts, the resistance of the thermistor is equal to 700 ohms. That's what we just calculated. Looking at our graph, it's resistance up on the y-axis, so we can go and find 700 ohms. If we look at how many boxes there are 10 boxes per 1000 ohms, which means one box equals 100 ohms. So if we've got 700 ohms, we need to count 700 boxes, not 700 boxes, 7 boxes up even, which takes us to this point just here, and follow this line along until we get to our curve. Excuse my wobbly line while I'm doing this. You can see we get to this point here. We now want to follow this down to the x-axis. Oh, again, got a very wobbly line there. Let's get rid of that. We get to 80 degrees C. Obviously, this will be a bit easier for you because you'll have a ruler on hand, but we can see that that is exactly 80 degrees C. So because this is just worth 1 mark, that's all we need to do to get to our final answer. Part B. The circuit is now connected to a switching circuit to operate a heater. Explain how the circuit operates to switch on the heater when the temperature falls below a certain value. So the key information they've given you just there in the sentence is explain how it operates when the temperature falls. This is going to determine our first sentence. So when the temperature decreases or when the temperature falls, we need to mention resistance. So when the temperature decreases, the resistance of the thermistor increases. We know that if there's an increase in resistance, there's going to have to be an increase in voltage. So again, being really precise, we want to say there's going to be an increase in voltage over the thermistor. You have to mention the thermistor. We know that if the voltage over the thermistor increases, that means the voltage over the MOSFET is also going to increase. And if the voltage over the MOSFET increases to the switching voltage, our MOSFET is going to turn on. So the voltage over the MOSFET increases, the MOSFET turns on. If the MOSFET turns on, this allows currents to flow to the relay, turning the relay on. This allows the switch to close, and therefore the heater can turn on. So we can summarize this in a sentence here. So the current flows through the relay, turning it on, closing the switch, and turning the heater on. There we go. I know that's quite a lot of writing, but it is worth 3 marks, and you need to mention the resistance, the voltage, and then the last point about the current flowing, the switch closing, and the heater turning on to get all of those marks there. Part 2. The resistance of the variable resistor is now increased. What effect does this have on the temperature at which the heater is switched on? You must justify your answer. So if we increase the resistance of the variable resistor, this needs the resistance of the thermistor to also increase to allow the voltages to still divide so the MOSFET can turn on. Writing this down, we can say increasing the variable resistance needs the thermistor resistance to increase as well. And this is so that the voltages can still divide. Remembering back to our V1 over V2 equals R1 over R2 equation, you don't need to put this into your answer, but just to clarify, if you increase R1, then you still need to keep this whole equation balanced, so you're going to need to increase R2 as well. Imagine saying 10 divided by 5 equals 20 divided by 10. Obviously both of these sides are still equal to 2. If you take 20 and make it bigger, let's turn it into 50 instead. If we do 50 divided by 10, we've now got 5, whereas it still needs to be 2. So we need to increase this 10 to 25 to make the whole equation still equal to 2. That's why if we increase our variable resistance, we also need to increase the resistance across the thermistor. And the easy way of saying all of this bit at the bottom is just to say to allow the voltages to divide. And this is so the MOSFET can still turn on. So I'm going to add that into my brackets there. To allow the voltages to divide so the MOSFET can turn on. Our last sentence we need to say is what's going to happen to the temperature at which the heater is switched on. If we start at a higher resistance, then it's actually a lower temperature that we're going to need. So this needs the temperature to decrease.